Okay, well, let's begin. You will be the only student taking this course, so there'll be flexibility in terms of teaching style. I'm going to start by giving some information about this course, and I'm going to cover chapters 1, 2, and 3 today. I'm expecting to give approximately 12 courses. They're going to be on Wednesdays and Thursday evenings between 7 and 9. My teaching style is, first I'm going to give a lecture. I'm going to cover the material in the lecture notes. And then in the second hour, if we need the whole hour, I'll be available to answer your questions or to talk about whatever you want. If you want to repeat that lesson or previous lesson, that's completely up to you. We don't have to use the full second hour if you don't want, if you don't have an hour's of questions, and since you're only one student, I'm guessing you won't have a full hour's worth of questions. We can finish early, that's completely up to you. I said a lecture will be approximately 60 minutes. Some weeks it'll be a little bit more than 60 minutes, some lessons I might be a little bit less than 60 minutes. I'm going to aim to be roughly 60 minutes each week, each lesson. We can break the material in this course up into 4 parts. Part 1 I'm calling an introduction. I'm going to talk about sets, symbolic logic, numbers, and Cartesian coordinates. Some or all of this will be familiar to you from high school. So maybe this can be revision. Part 2 is about geometry. Part 3 is about finite maths. And then in the final section, we'll talk about calculus. I'm expecting to use 2 lectures for the first part, 3 lectures for parts 2 and 3, and 4 lectures for calculus. I've written lecture notes for this course. You can find it in the content section. The lecture slides and the lecture notes will be very similar. So if you want to follow along the lectures, or if you want to read before or read after, you can print out the lecture notes. I'm going to examine this course with homework and 1 midterm exam and 1 final exam. So assuming that we don't hear anything from head of the university, the homework will be worth 20%, the midterm exam will be worth 20%, and the final exam will be worth 60%. The homework will be multiple choice tests on OLAN. I'm going to set the deadline for all of the homework to 1 day before the final exam. So if you really wanted to, you could wait until the end of the course before doing the homework, but I think that would be a bad idea. I would advise you to try to do 1 or 2 pieces of homework every week. Check that you're not having any problems with them, check that you're understanding everything, while there's still time to ask me if you need help, or ask technical support if there's any technical issues. So I encourage you to try to do the first piece of homework this week, next week to do 2 homeworks, and so on. The midterm exam will be an online exam, as will the final exam. If this was a classroom course, then I would expect to be giving 8 hours of lectures to you every week. And for each hour of lecture, I would expect you to study an extra 1 or 2 hours outside of class. So we should think of this as between 16 and 24 hours of work each week. For an online course like this, in class time we've got scheduled 4 hours, and therefore for your other study I would be expecting you to study somewhere between 12 and 20 hours. I know that if I was in a classroom, how much material I would cover in 8 hours, and I know that I can cover the same amount of material in about 2 hours if I use online teaching methods. So we're going to have spare time in our 4 hours to do whatever you want, to repeat or to answer questions or to finish early if you want to. For the other study, there's going to be the homework tests for you to do. We're recording these lectures. You can watch them on Okan, and I'll also upload to YouTube in case that's easier for you. You should be spending time reading the lecture notes or the lecture slides. The lecture notes have lots of problems in for you to work on. You should try to solve as many of these as you can. There are answers to most of these problems in the back of the lecture notes, so you can check if you're understanding the material correctly. There's a discussion board where you can ask questions to me, or you can send your questions by email if you wish. You should be reading books about maths during this course. I'm going to suggest a couple of good books that you might like to read, or you might like to watch online videos by other lecturers. For example, there's a lecturer who calls himself Black Pen, Red Pen on YouTube, and he has some nice calculus videos that you might like to watch. These are two good maths books, Thomas's Calculus and College Mathematics for Business, Economics, Life Sciences and Social Sciences. You don't have to buy these are optional books. You might find these useful or you might not. If you look in the bottom corner, you see there's a slide number. This will give you a rough idea as to how far I am through my lecture. And if you do print out the lecture notes and you're following along, I'll always put the chapter title at the top so you can quickly find where we are. Chapter 1 is about sets. Hopefully this chapter will be revision for you from high school, but of course you might have forgotten it. A set is a collection of objects specified in such a way that we can always tell whether a given object is in the set or not in the set. For example, the set A, which is the set containing 1, 2, 3, 4, and 5. This is a set. The set B containing apple, banana, and cherry is a set. And the set C, which contains the letters N, E, I, and L, is a set. This symbol, this strange letter E, means is in the set. So for example, if B is the set, apple, banana, cherry, we can say that banana is in this set, but date is not in this set. Each object in a set is called an element of the set. If we have a set without any elements, we call this the empty set. And we have a special symbol for the empty set. It's a circle with a line through it, like this. Here's another symbol which I'm going to be using, this vertical line. This vertical line means such that. Here it is. The set of X such that X is a weekend day. This is the set containing Saturday and Sunday. Or the set of numbers X such that X squared is equal to 4. We know this must be the set containing the numbers -2 and 2. The set containing all of the people who are more than 5 meters tall. There's nobody in the world who's more than 5 meters tall. This is the empty set. Let's suppose we have two sets, A and B. And let's suppose that every element inside set A is also in set B. Then we can say that set A is a subset of set B. And we have a special way to write this. We write it like this. A is a subset of B. So for example, the set containing the numbers 1, 2, and 3 is a subset of the set containing the numbers 1, 2, 3, and 4. Look at the left set. 1 is also in the right set, and that set number 2 is also in the right set, and the number 3 is also in the right set. Set containing 1, 2, and 3 is a subset of the set containing 1, 2, 3, and 4. Likewise, the set containing banana is a subset of the set containing apple, banana, cherry, and the set containing Neil and Sezgin is a subset of the set containing Neil and Sezgin. These two sets are the same, so one is a subset of the other one. This satisfies the rule that every element of A is also in B. Every element of the left set is also in the right set. The universal set is the name for the set of all the elements that we are considering. And we call this set U. So for example, we might have a picture like this. This rectangle is the set U. This is everything that we're thinking about at the moment. And let's suppose that A and B are subsets of U. And let's suppose that A and B overlap somehow. Some elements which are in both A and B. The union of A and B is every element which is in either A or in B or both. In this picture, the union of A and B is everything which is coloured in blue. The intersection of A and B is the elements which are in both A and B. For example, ABC union BCD, we want the set which contains everything which is in ABC and everything which is in BCD. So that's A, B, C, and D. The intersection means we want the elements which are in both sets. A is in only one of the sets, D is in only one of the sets, B and C are in both the sets. So the intersection is the set containing B and C. Now to talk about the complement of a subset. This is everything which is not in A. So for example, if U, that's the set of everything that we're thinking about at the moment, is the set 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and suppose that A is the set of odd numbers in U, then the complement of A is everything which is not in A. That's the even numbers, 2, 4, 6, 8, and 10. That's enough about sets for now. We'll need this notation later. Let's talk about symbolic logic. A proposition is a statement which is either true or false, but not both. For example, grass is green. This is a proposition. It's a true proposition. 2 plus 5 is equal to 5. This is a proposition. This is a false proposition. My name is Neil. This is a true proposition. But close the door. We can't say that this is true, and we can't say that this is false. This is not a proposition. Is it cold today? This is a question, it's not a proposition. We can't say that this statement is true, we can't say that this statement is false. We could answer yes or no, but we can't say that the statement itself is true or false. And 1 is not a proposition. 1 is not true, 1 is not false. 1 is just a number. The symbol for or is this type of V. For example, if P is the proposition, it is snowing today. This is a proposition because it might be true, it might be false. And Q is the proposition, it is raining today. It might be true, it might be false. Then P or Q is the proposition, it is snowing or raining today. M is the proposition, X is in A, and N is the proposition, X is in the set B, and M or N is X is in the set A or X is in the set B. Or to write it another way, X is in A union B. We can understand or using a truth table. We have 2 propositions, P and Q, and each one of them can be true or false. So we have 2 multiplied by 2 or 4 rows in our table. We have all of the possibilities. True, 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 false, false, true, or false, false. Now I want to consider the third column, P or Q. This means P is true or Q is true. At least one of them needs to be true. For the first line, we have true and true. P or Q, is at least one of them true? Yes, true. P true, Q false. Second line now. Is at least one of P and Q true? Yes, P is true. So P or Q is true. Likewise, row number 3, is at least one of P and Q true? Yes. So P or Q is true. And then the final line, if P is false and Q is false, we ask P or Q. Is at least one of them true? No. So P or Q must be false. The symbol for AND is this upside down V. Like the symbol for OR, but turn it upside down. For example, if P is the proposition I am hungry, and Q is the proposition I am sleepy, then P and Q is I am hungry and sleepy. Or in terms of sets, if M is A, X is in the set A, and N is X is in the set B, M and N is X is in the set A and X is in the set B. So X is in A intersection B. If you're trying to remember which symbol is OR and which symbol is AND, try to remember that they open the same way as the union and intersection. A truth table for AND. AND means we need both P and Q to be true. First line, are both P and Q true? Yes. So P and Q is true. Bottom 3 rows, are both P and Q true on any of these rows? And the answer is no. These are all false. P is true and Q is false. At least one of them is false, so P and Q must be false. Likewise, if P is false, P and Q must be false. False, false, P and Q must be false. The symbol for not is this symbol. It's not quite a minus sign because it has a little vertical point on the right hand side. So for example, if P is the statement, your teacher likes coffee, then not P is the statement your teacher does not like coffee. If M is the proposition X is greater than or equal to 7, then not M is the statement X is strictly less than 7. Truth table for this is quite simple. If P is true, then not P, that the opposite of P must be false. If P is false, then its opposite must be true. The symbol for if and only if, which in maths we like to abbreviate as IFF. This is not a real English word, this is only a mathematical English word. And the symbol for if is this double-ended double arrow. And this means P and Q are the same. They're either both true or they're both false. Look at the first line. Are P and Q the same? Yes, they're both true. Therefore, P if and only if Q is true. Line 2 and line 3. Are P and Q both the same? No. One is true and one is false. So P if and only if Q must be false. And then bottom row. Are P and Q the same? Yes, they're both false. Therefore, P if and only if Q is true. The symbol for implies is this rightwards double arrow. For example, if P is the proposition I'm in London and Q is the proposition I'm in the UK, then P implies Q. If P is true, then Q must also be true. Let's look at the truth table. First row, people are usually happy with. P and Q are both true. Does P imply Q? Then yes, that's true. Let's look at row 2 and let's use the example of London and the UK. Let's suppose P is true. Let's assume I'm in London. And let's suppose Q is false. I'm not in the UK. Is it possible to be in London but not be in the UK? No. This row must be false. Now this is where people usually wonder about this. Let's suppose P is false and Q is true. I'm saying that P implies Q is true. Implies is only valid if P is true. If P is true, then we must also have Q is true. If P is false, then we don't care about Q. Q might be true, Q might be false. We don't care. Let's go to the example. Let's suppose P is false, but Q is true. Let's suppose I'm not in London, but I am in the UK. Is that okay? Yes, there's lots of cities in the UK. I might be in one of the other cities. It's okay to be in the UK, but not to be in London. And bottom line, suppose both P and Q are false in the previous example. Let's suppose I'm not in London and I'm not in the UK. Is that okay? Of course it is. There's lots of countries in the world and there's lots of cities outside of the UK. So the bottom line is okay. Bottom line must be true. Before we go on, let me remark that we can only write things like P implies Q if both P and Q are propositions. So don't write nonsense like this. The integral from 0 to 1, 3x squared dx is square bracket x cubed from 0 to 1 implies 1. First part is okay. The part in the orange box is a proposition. In fact, This is a true proposition. The problem is 1. 1 is not a proposition. We can't write implies 1 because 1 is not a proposition. What we wanted just here was an equal sign. If I had written equals just here, then it would be mathematically correct. If P and Q are propositions, then P or Q, P and Q, not P, P implies Q, and P if and only if Q are also propositions, because then we can also say true or false for each one of these. I suppose we want to go backwards. There's 2 ways to go backwards. The converse of P implies Q is Q implies P. There's another way to go backwards, which is more interesting in mathematics. This is called the contrapositive. The contrapositive of P implies Q is not Q implies not P. Later today, I will explain why this is mathematically interesting. For example, if P is it is raining and Q is I get wet, then P implies Q means if it is raining, then I get wet. Converse is if I get wet, then it is raining, and the contrapositive is if I do not get wet, then it is not raining. There are 22 identities to talk about. These start off quite easy, but as we get to the end of the list, I'm going to need to be explaining those in more detail. P or P. Is P true or is P true? If P is true, this is true. If P is false, this is false. This is exactly the same as P. P and P. If P is true, both sides are true. If P is false, both sides are false. These are the same. P or Q is the same as Q or P. It doesn't matter which way we write them. P and Q is the same as Q and P. Likewise with 5 and 6. If we have 3 propositions P, Q, and R, doesn't matter which order we calculate ors or ands. P or Q or R is the same as P or Q or R, and the same and. If I have something like not P or Q, I can take the not inside the bracket, but the symbol or needs to change to an and symbol. Likewise, for line number 8, if I take a not inside the bracket, the and symbol must change to an or symbol. Lines 9 and 10 are perhaps straightforward. We know for numbers, for example, if I wrote A multiplied by B plus C, we know that this is the same as AB plus AC. We can do the same thing for or and. We can multiply them out like this. Line 11 is quite straightforward. P or true. By true, I mean something, a proposition which is always true. On the left side, if P is true, we have true or true, which is true. If P is false, we have false or true, which is true. This is always true, so P or true must be true. 12, 13, and 14 I'm going to leave for you to think about. P and false is always false. P or false is the same as P. P and true is the same as P. Let's move on to 15. P or not P. For or, we need at least one of them to be true. If P is true, then we get true. If P is false, then not P is true. So at least one of them is true. This must always be true. P and not P. Is it possible for both P and not P to both be true? No, this is always false. Not P. P, that's straightforward. But now it starts getting a little bit more complicated. P implies Q. I'm saying it's the same as not P or Q. P if and only if Q is the same as P implies Q and Q implies P. Well, that sort of makes sense judging by the notation because we have double pointing arrows for if and only if. So it makes sense that that means P implies Q and Q implies P. Number 20. P and Q implies R is the same as P implies Q implies R. Okay. 21. P implies Q and P implies not Q. I'm saying it's the same as not P. And P implies Q. I'm saying it's the same as not Q implies not P. This is contrapositive. I said why? Why? I said before I explained why contrapositive is useful in mathematics. Because not Q implies not P is the same as P implies Q. Sometimes in mathematics, when we're trying to prove that a fact is true, it's very difficult to prove that P implies Q is true. But sometimes it's easy if we turn it around and then instead we prove that not Q implies not P. And then just from this fact by symbolic logic, if we can prove not Q implies not P is true, then we also know that P implies Q is true. Let's prove number 18. That's this one. I want to prove that P implies Q is the same as not P or Q. And I'm doing this with a truth table, one big truth table. Start with all of the possibilities of P and Q. True, 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 false, false, true, or false, false. And then we fill it in. P implies Q. We've looked at this already. We can just copy from the previous slides. True, false, true, true. I need not P. Not P is always the opposite of P. If P is true, not P is false. If P is false, not P is true. And Q, I'm just copying over. Just copying over. And then I'm just going to look at the right half of the table now. Not P or Q. Is at least one of not P and Q true? Q is true, so yes, true. If we have false, false, we must have false. If we have true, true, we get true. True and false, at least one of the bottom line is true, so we must have true. But then, look what we have. This column goes true, false, true, true. And this column also goes true, false, true, true. These are always the same. That means that these two logical things are the same. P implies Q must be the same as not P or Q. I can also prove identity 22 the same way. This left side is the same as we just had. P implies Q, true, false, true, true. I've written not Q, that's the opposite of Q, and not P. And then I've calculated not Q implies not P. And again, I get true, false, true, true. So these two things are the same. Before I finish this chapter, a little bit more notation. The symbol for all, and the word all, of course, has the letter A in, is this upside down capital A. The symbol for there exists starts with the letter E, is this backwards capital E. We'll be using these later as well. The final chapter for today's lesson, I think, is about numbers. What are the basic numbers, the first numbers that we teach children when the children first go to school or before they go to school? We teach them the numbers 1, 2, 3, 4, 5, 6, etc., etc. These numbers are called the natural numbers. And to describe this set, we use this special letter N, hollow stroke. So, for example, 2 is in N, or 2 is a natural number. 7 is in N, 7 is a natural number. A half is not a natural number. 0 is not a natural number. Just to be careful here, there's a little bit of disagreement in the world. Some people think that 0 should be a natural number, but most mathematicians agree that 0 is not a natural number. And -5 is not a natural number. In the natural numbers, we can do addition and we can do multiplication. What I mean is, if we take 2 natural numbers, let's say 2 and 7, add them up, we always get a natural number. If we multiply 2 natural numbers together, we always get a natural number. But we can't do subtraction in the natural numbers because, for example, 2 minus 7 is not a natural number. So what can we do? What did humans do in our history when we wanted to start doing subtraction? Humans invented new numbers. And the numbers that we invented was the integers. That's all of the natural numbers, 1, 2, 3, 4, 5, etc. And now we're going to allow 0, and we're also going to allow the negative numbers. The symbol for the natural numbers is this special letter Z. Why is it a letter Z? It comes from the German language. In Z, we can do addition and subtraction and multiplication, but we cannot do division. Add 2 integers together, we always get an integer. Do an integer minus an integer, we always get an integer. Multiply 2 integers together, we always get an integer. But if we do integer divided by integer, sometimes we do not get an integer. So what do we do? What did humans do in our history when we first encountered this problem? We invented new numbers. And the numbers that humans invented to be able to do division, or to always be able to do division, as long as we're not divided by 0, is the fractions. That's the set of all of the fractions, or the set of all the numbers a divided by b, where a and b are integers and b is not 0. And this set is called Q, for the English word quotient. This set is called the set of rational numbers. For example, 0 is a rational number, 1 is a rational number, 3 divided by 4 is a rational number, 10 over 13 is a rational number. But pi is not a rational number, square root of 2 is not a rational number, etc. In Q, we can do addition, we can do subtraction, we can do multiplication, and we can do division, as long as we're divided by a number which is not 0. So we ask, are we happy now? Do we have enough numbers to be able to do mathematics? And the answer is no. Why? Why are we not happy? We're not happy because Q has holes in it. What I mean is, if we try to draw a picture of Q, then we would have all of the numbers drawn in a line, but the line would have lots of holes in it. For example, there's a hole here at the square root of 2, because the square root of 2 is not a rational number. There would be a hole just here where pi should be, because pi is not a rational, and so on. In fact, Q has infinitely many holes in it. So what do we do to solve this problem? What did humans do in our history? We invented new numbers. And we invented the set of numbers R, which is the set of all numbers which can be written as a decimal. For example, 0 is a real number. 23 over 99 is a real number. 3 over 4 is a real number. Pi is a real number, and so on. Any number like this that you can think of to write as a decimal is a real number. The real numbers are complete. This means if we draw all of the real numbers in a line, then there's no holes in the line. So I asked the same question that I asked before. Are we happy now? And the answer is yes. Now we're happy. Now we have enough numbers to be able to do mathematics. And that brings us to the end of this week's lesson. This week was a shorter lesson because it was the first one, but from tomorrow onwards, they will start to get a little longer. Tomorrow's lesson, I'm going to talk about intervals, Cartesian coordinates, functions, and sigma notation. Do you have any questions?